Okay, welcome back. It's me again. So you know me. Also, you cannot see my badge, but um, uh, so this time I'm pretty much okay with the printout. You see also from the date that I did not change too much from 2 years ago. Okay. Let's get started now about silicon heterojunction solar cells. I put at the beginning a little bit material from my lecture at the university. So we have some information on how you get to the silicon wafers and so on, a little bit on general silicon solar cells. So it's maybe some things you had seen before from the talk yesterday on silicon perspectives, and then we'll a little bit talk about our activities in Jülich. So it's say not as strict outline as it was in my two previous talks. It's more relaxed. So. Also have some nice animations, but this time I didn't do them myself, so there was somebody doing this. First, this important point for silicon is that we're dealing really with an abundant material. That's the second most frequent element that we have on Earth's crust, and first question is, I mean, you get all the silicon from sand, so it's silicon oxide, and you need to get, first of all, rid of the oxygen. Yeah. Yeah, that's okay. For me, it feels not like I have a microphone, so it's anyway. Okay, so the reaction we need, so we need carbon, and we produce a little bit carbon oxide to get rid of the silicon, and that's a one high temperature process that you have to account in the, say also in the energy balance of crystalline silicon, that you need the energy to get this to get the silicon. It's done as a large industrial process in arc furnace to get the first stage of what we finally have as electronic grade silicon or photovoltaic grade silicon. But first of all, we have silicon, but it's only 98% pure, so it's not something that you can use for any electronic purposes. So in the next step, you need to purify this material to get electronic or photovoltaic grade polysilicon, and you see that the purity now is getting much better, and you need essentially it's a distillation process. So you gasify silicon by HCl into silicon hydrochloride, and that leaves behind a lot of the impurities, and then you resolidify this material in a chemical vapor reaction to get the silicon back, but with less impurities. And if you repeat that several times, you're getting to that electronic grade polysilicon that now has the purity we need. So you remember, maybe when we're talking about defects, we're talking about critical concentrations from, say, 10 to the 16 per cubic centimeter, 10 to the 17, but depending on the type of impurity, it must go down to 10 to the 10 per cubic centimeter. And then you compare that number with the number of atoms you have, a number of silicon you have in the same volume, it's 10 to the 23. So you see that a lot of nines is required that we get a material that we can use for solar cells. So then you, let's see what is, so how we get to the wafers. So what we like to have is either monocrystalline silicon wafers, and that's what in general is needed for the silicon heterojunction solar cell, because it's a high efficiency technology. So you don't want to have a lot of grain boundaries that you have in the multicrystalline silicon. What you get in a simpler process as compared to this single crystals from the Joukhalski or from the float zone process. It's fair to say at the moment that also people working on block casting, that's a process that is cheaper, also have a lot of tricks now to make the multicrystalline silicon not look like that, with a lot of grain boundary, single grains. You can see the single grains, so they are in a sense macroscopically. That's why it's called multicrystalline and not polycrystalline, as we're talking about CIGS or cadmium telluride or perovskites, where the grain size is in the order of micrometers or even below. Here we're talking about grain sizes in the millimeter range. So the grains are quite big, but still there are grain boundaries in that in the case of silicon lead to a lot of recombination. And as you have hopefully learned yesterday, recombination is bad, except for the radiative one that you cannot avoid. And the less grain boundaries you have in the silicon wafer, the better. And people also have now really very, very big grains, and the quality of the multicrystalline silicon, for the grain size at least, is approaching that of the monocrystalline, where you have no grain boundaries at all. So there are essentially two processes to get to single crystalline wafers. The first one, and that's a commercial one, is a Joukhalski grown material. So that's name complicated to spell, and it's named after a Polish scientist, but who lived, I think, in the Soviet Union at that time, and I think he spent a lot of time just growing crystals. And the way you do it is that you melt the polysilicon in a crucible, and then you start with a seed layer that you dip into the melt, and then you start pulling and turning so that you get a very regular, slow, nice process, so that you can grow one single crystal and you pull it slowly. Let's see whether we have, oh no. Yeah, you can see it here. It's the ingot. There's no person on that, but I can tell you that the ingots are like 4 meters or 5 meters long, so it's made in big halls, and that's all one single crystal. So that's easy to say that any atom here at the top is knowing by multiplying the distance where another atom is at the other side of the rod. So that's really a fascinating thing, that you can have such large single crystals. The other method is a float zone. So there you start already with a rod which is made from polysilicon, and you transform this polysilicon into a single crystalline material by just melting it in this floating zone here. So you move the heater up and down. And when there's also a seed here, so when you start here with melting, so the growth becomes epitaxial in that sense that this seed gives the crystal direction of what you have finally as a big single crystal. So the difference between these two is, and you're going up and down several times here. The big difference between the two methods is that you here using a crucible, so you put the silicon into something, and it's very hot. This, of course, the melt, and you cannot avoid that atoms from your crucible go into your void, in your melt, and then you having especially in a sense reintroducing oxygen from the crucible into so took a lot of effort to remove the oxygen from the sand in at the first place, but now some of the oxygen goes back, and also carbon from the crucible. So you have an amount of impurities in that material that you don't have in the float zone material for two reasons. First, there is no contact to anything, so there's only a protecting gas, nitrogen gas, that is around this rod. First thing, so you have no contact. And the second thing is that by moving up and down this melt, because solubility of the impurities is different in the melt and in the solid phase, you shift all the impurities to the ends of the rod. So normally also you get the best quality wafers from the middle of the rod, and you just reuse the top end and melt it again, and or throw it just away, or sell it to you very cheap. You can also do that. Yeah, and then doping. We were discussing several times how important doping is, and you can do this doping during that process just by introducing, for instance, phosphorus to get N doping, or boron to get P doping. So now come the nice applications, animations that don't stem from me. So let's go again through the history. We had this yesterday already, but now we have this nice picture, so we can figure out much easier and in 3D. So it's this quasi 3D. So I mean, the history of silicon solar cells is pretty long. So it started with the first publication of say a power device in 1954 from the Bell Labs, and say to my frustration as a researcher, I could say these guys made essentially the same thing as we do nowadays. So they understood everything. They understood what is a PN junction. They understood what are the issues with their device, and they also, if you look at the press at that time, they're unfortunately not here, but there is an article in the New York Times that device made from sand will secure our future energy supply. That's it. 1954. Now we're still not really there, but we are pretty much closer. So that's really, really nice. So what was the point at that time? So that's from 57. Also interesting thing with efficiency, you can see history in that efficiency curves. So it's not only scientific history, as for instance, yesterday was pointed out for the CIGS, that you see the different technological steps, but you see also the changes in politics. Essentially, there are two steep rises. And the first rise is coming from what denoted at that time the Sputnik shock. And the Sputnik shock was when the Soviet Union sent a satellite to space before the Americans did. And that was a big shock, and they started to catch up and to be first on the moon. But for all the satellites, for most of the satellites, you need PV to power something there. And that's why this systematic research in those times led to the increase of efficiency. And the second here is coming from the 80s, and that's another shock, that's the oil price shock. So in that time, people say, okay, oil is not so cheap as it used to be, and it's a mean of political power, and so we have to do something about that. And then a lot of research money went into saying, bringing this PV technology down from space to Earth, and that's what was going on in the 70s and in the 80s. Okay, but back to the device. So at that time, in the very early stage, it was relatively simple. So you started at that time with N-type silicon. You made the boron diffusion, and as we have learned yesterday, okay, if you make the diffusion, you have the P-type material all over the edges of the wafer. So and as we have also learned yesterday, that's no use to have only one single contact to a solar cell, because you need N, a plus and a minus. So you have to remove the P-type silicon at, it's not very clearly seen, but the P-type wraps around until approximately here, and then it's removed here, and you just get metal on the N-type. So it was a IBC solar cell, back-contacted solar cell. Sunlight is coming from here, so it's took 50 years to come back to the basic idea to have both contacts on the back, but it was already there at that time. Another frustration, so nothing is new, what we're doing. Okay, but the thing is, you got a very simple ohmic contact just by doing the metal on the silicon, on both types of silicon. And there is really an important issue with that, because if you're doing a metal on silicon, so does anybody know which type of contact you're making? Is this just doing a metal on a semiconductor gives you an ohmic contact? Pardon? Yeah, so the keyword that I wanted to know is Schottky contact. So because my contact institute, my university is the Walter Schottky Institute. So in Germany, we're very proud about Walter Schottky, and we can also say that, okay, this guy really invented semiconductor-based physics, semiconductor-based devices. So he was also maybe the first guy who found out that there is a strange behavior in general. If you put a metal on a semiconductor, you have a large capacitance. We were discussing the capacitance last time, and that's he said he did not invent the name space charge region, but he said, okay, there is a barrier region that is forming about, and that's the Venn diagram of a Schottky on P-type Schottky contact is like that. So that's the metal, that's the semiconductor, that's P-type, and that's the space charge region. And the bad thing about the electrons and the holes at that point is, I mean, in a sense, you can make a solar cell, a Schottky type solar cell on that sense, because, okay, some selectivity, so the electron wants to go there, the hole is a little bit inhibited to go there. So that would be a Schottky contact on P-type. But then if you have your PN junction here, you got a problem. Because now electron can go out everywhere and the hole can go nowhere. So it's not the selectivity you want to have. And if this metal contact is supposed to be not the electron contact, but the hole contact, you're having really a problem. And that's then actually you are better off if the doping is somewhat high of this material. For the holes, there is an advantage. Has somebody a magic word for me? How can I get out the holes through such a barrier? Tunneling, exactly. So if you have a very high doping, this space charge region gets very narrow. So the hole has a chance. So if it's 2-3 nanometers, there that's thin enough to get the hole tunneled out of the device. And if you do the doping here at that region higher than in the other region, you get another advantage, and that's to get another small step in your band diagram. No, I don't. It's exactly so. The should be parallel. So that's a higher doping at the close to the contact. So you're getting a barrier, at least a little bit of barrier. So still, you have recombination then. Recombination means, okay, electron meets hole. And it's also considered recombination if they meet on the contact, so then they don't care. So if they meet here, and it's also recombination, they vanish, but in the contact, the same thing happens. So that's the point why it's bad to have a metal on the semiconductor directly. So, but at those times, the people were very happy with doubling of the efficiency. They send the satellites to space, and then we're thinking about further improvements, and that's the typical space cell. And you see now the contacts are on both sides. You now have a starting point is a p-type silicon, and you make the n-type junction by diffusion. You have the metal grid. And already there, people cared about how getting the light into the device by adding an anti-reflective coating to the material. So what happened is with the grid contact, the resistance reduction. So we get a nicer fill factor, and we improve the JSC. So then, okay, so then people start to care about this back contact issue to improve the selectivity of the back contact, and also they reduced the thickness of the n-type silicon wafer, and that's another issue that will come up later. That at those times, why this cell looked violet. I know it has nothing to do with that. That still there's a lot of recombination at the interface here between the anti-reflective coating and your n-type layer. So at those times, people did not expect that you get any current out of light that is absorbed in the n-type material. So because it was highly doped on the one side, so you get a lot of Auger recombination. And also because you get a lot of surface recombination here. So if you make that thinner, that layer, less light is absorbed. That is not contributing to the photocurrent. That was the one thing. Then the doping went higher, and in some poster we had yesterday discussion about the interdependence of doping and VOC. So if you have a higher doping concentration at the same generation recombination rate, you can get higher VOC. Okay, that's still there. So, and then light trapping improved. That is why it turned from violet to black. So you absorb more light. The cell looks more black, and that's when people saw that anti-reflective coating is not enough to reduce reduction, but you need surface texture. And then that was metal insulator NP. Okay. First of all, okay, now people notice that we can get reduce this recombination at the top of the N-type layer by introducing a passivation layer, silicon oxide, and the question is in principle, okay, and then it's also a concept that is now coming back, that it's not necessary here to have the metal immediately on the semiconductor here, because if this insulator is thin enough, also the electrons can tunnel through this insulator, and that's brought the thing to 18%. So, but still okay. Then what is next? So that's to get to 20%. So then, okay, this was opened again because maybe the silicon oxide could not be so well controlled, so that maybe you can reduce the resistance, but just by opening, but you preserve the passivation layer over most time, but only there where you have the contact, you have the contact from the metal to the semiconductor. Then you see the shape of the texture has changed, so this is now turning to inverted pyramids, and I can tell you after a lot of light trapping simulations, that's almost the best thing you can have as a anti-reflective or light trapping texture. So that's we have a special session on light trapping, but that's also, of course, the textures does not only reduce reflection, but also enhances the light path of the weakly absorbed light inside the solar cell by randomizing it or by having steep directions and keeping it a lot of time in the solar cell. That brought people to 20%, and then still this small contact to the metal was not good enough. Then it was that's a perk, and now you see how long ago that is, but is now entering into industry. So it takes 20-25 years until this idea is becoming a part of the industry. But the physics behind is very, very clear. Also at that time, people, if you look at the scheme, at how at that time this type of solar cell has been made, it was like 25 process steps with photolithography, forth and back, and to get all this, every detail here included a full photolithography process. So that's to make this. But it was demonstrated how, based on a physical understanding of the device, you can push the thing to the limit. First place, you do not look whether that can be made in industry, but you just want to show that physics works. And how does physics work here? So, as I've shown here, the higher doping is making a better contact between the metal and the semiconductor. On the other hand, you like to have the doping of the rest of the emitter here not so high. So people may ask, why not having the N plus all over the place? The point here is, if with that high doping, you're also introducing a lot of Auger recombination in the emitter, also very thin, a few hundred nanometers, half a micron. But still, I mean, most of the, lot of short wavelength light is really absorbed in the first few micrometers of the material. And if you have a considerable recombination here, you don't like it. Also, it's still, if you go into very high doping, also there is an important thing to consider that not every doping atom that you put in your material gets to the right place. It goes to the right place if there are few, but if you go to the 10 to the 90 to 10 to the 20, you get a lot of phosphorus atom. In that case, they're not sitting replacing the silicon, but they are interstitial, and that's something that does no doping, but does shockley retard recombination. So a part of the recombination, high recombination probability of highly doped silicon is not because of Auger, but because of interstitial doping atoms. And it's very hard to find out, to analyze this, but it's of course very important to understand the mechanism, because we are now already on a very, very high level compared to the Auger limitation of silicon of 29%. So you have to look at every detail. And the other feature here is that you have this partial rear contact. So you have still issues with the metal semiconductor contact. So why not restricting this to the absolute minimum that you need to get the holes out? So, and minimizing recombination by having only a small area. So that's a nice optimization problem. So if you have no holes, of course you have no majority carrier current. You have to optimize the distance, because the holes have also find their way to this contact. But you can reduce the effective contact area by a factor of 100 roughly. So that's only 1% of the back surface area is covered with a metal. So, and then the last trick, and this makes PERC to pearl, is that still there you can have this trick improvement that you have a higher doping P plus at that point to reduce recombination even more, and to also enhance the conductivity at that point. And that's the 25%, which is at the beginning of this century, and you see now with the 26%, it took quite a while. So that flattened up. But then other things came up. There's a partial, very small improvement in terms of efficiency, but it's a very big step within this 15 years, because this is really something that is, again, simple, so that its time to industry is much shorter. I mean, that was reinvented, I would say, maybe 7 years back. It was not really invented there, but it was reinvented. It was there also in the 80s, so everything was there in the 80s, except of some of you, but yeah, so I mean, the point is really look up the paper that have been written before you have been born. That's maybe rule number one. So not there was science before your birth, so that's an important science. So that's okay. So now things have turned around again. We have the N-type silicon here as a starting material. So the top contact is now the PP plus. So it works the same way. For the passivation, there is a new material. It's also not new. It was also around in the 80s. Aluminium oxide that makes a good passivation, but you have this P plus and you have this contact. So there are also very nice tricks to have this P plus here in an industrial process. You need not to do nowadays to have the photolithography and to do extra diffusion. You just have the additional doping in the paste of the metal. So it's just all putting, I mean, the major progress here. So you see that in this time there was not much efficiency improvement, but in that time, during those 15 years, photovoltaic got really, really, really cheap. That's what is happening there. And it got cheap because those 20 process steps were condensed to 3. So each of the process steps in preparing a silicon solar cell serves a lot of different purposes. So that condensed to this few, and that's making the process lean and cheap. Okay, but okay, back to the physics here. It's okay. In principle, nothing has changed in the front except for exchanging the type of doping, and also this inverted pyramid. So there's still no cheap way to make an inverted pyramid. So and the random pyramids they just get by dipping the wafer. And you have to optimize the process, but it's fairly simple. The random pyramids just by dipping in KOH under optimized conditions. It's doing a pretty good job. It's even that is hard to beat. It can be beaten by several expensive structures, but it's quite good. So there's not much scope for improvement with this skill. Okay, but the big change now coming here at the back contact. So you have no more structure here, but what you have here now is again a silicon oxide between contacting the or on all the back surface area, and that's a very thin and a very simple silicon oxide. It's a wet chemically made silicon oxide. That's at fairly low. It's at more or less at room temperature. You heat it a little bit to 60 degrees or something, but you get a very nice silicon oxide, which is very stable. On the other side of this silicon oxide, you get another N plus silicon, but which is now deposited, for instance, by CVD on the other side, and then you have the metal. So the thing here is that again here there is no direct contact. There is a contact between the metal and that polysilicon, but that's not the absorber material. The absorber material is here. So you have not, on that case, you have not this Schottky contact on the absorber. So you have not that issue, which you can work around a little bit with a compromise. But you have an additional layer in between. And talking about band diagrams, so that's just having this. It's very simple. So that's because you have N-type silicon on both sides. That's the silicon oxide. N-type on both sides. So that's maybe here's a little bit higher dope. So it looks like that. And that's poly. That's mono. N plus N. So still we have the issue, separate the electrons from the holes. Why is this working here? I mean, that's thin, so electrons can tunnel through. That's okay. But why the holes? It's also thin for the holes, so it's not that you... Actually, what you can't do in a band diagram is having something different on top, and that would be nice. I can make it broader only for the holes, but that's not possible. So what? Why the holes have a hard time to penetrate through that barrier?
Barrier energy is different.
Exactly. That's the point here. So that it's for tunneling, it's not only important how thick your barrier is, also how high it is. That's different from the tunnels we have here in the Alps. So once the tunnel is thick, you drive through. You don't care about the mountain, which is on top. Can be 20 meters, but can be also maybe 2,000 meters. So for the tunnel here from to Italy, it's like you have the entire Mont Blanc on top of you. So in this tunnel you don't care, but the holes do care about the mountains here on top, and that goes really exponentially, the tunneling probability with a height of, and that's because in silicon oxide the band offset on the valence band is much higher than on the conduction band, and that's why silicon, by just its material properties, is nicely selective for electrons. Okay, and that now coming to, yeah?
And that's applied for also for holes. This is working for electrons.
That's working for, yeah, so big question is why does it also work for holes? Not as perfect as for, but you can in fact do the same thing, same contacts. You can replace that front contact also with silicon oxide and P plus, so you can bring in principle the silicon oxide here in between, and then having a P plus layer on top, which does also work, and in contrast to what I said here, in principle it could not work because the holes cannot penetrate, and people are thinking that because the silicon oxide for that side would be a little bit prepared in a different way, and the theory or explanation at the moment is that this silicon oxide is not really having some pinholes, and if you have the pinholes, you're coming back to this point contact scheme on another scale. So in principle it's believed that, okay, you have the silicon oxide, which is not really uniform and sometimes also missing. And then if it the barrier gets even thinner, or it's just not there, the holes can penetrate. So it's not really the perfect physical thing you want to have, but it somehow works at least as good as you would do this compromise with this point contact. So the point contact is also a consequence of you have not a perfect solution, but with compromising area you can have a kind of workaround. And the other theory is that if you're making this silicon oxide slightly unstoichiometric, you introduce defects here, at least electronic states. You have to think about that. All this thing is only 3, 4, 5 atomic layers thick, so there is a lot of disorder. And if you're playing around a little bit with the stoichiometry, you can make, even if you have no physical holes in that sense, but you can make this electronically more look like Swiss cheese, so that the holes can also penetrate via the defect. So that's good question. So that's a matter of research. So then with the same efficiency, so that's a nice animation here, because it's our field. So I thought, what is this? Do we have nowadays solar cells that you just simply wafers and they beam the energy somehow into? No. Okay, I got that. Okay, so that's now say the really it also stems from the 90s, so most of you were already born but did not care about heterojunctions at that time. But this record came also in 2015, and that's a radically different concept because all these issues with the metals and workarounds is no more there. So now how it works, so you start with texturing the wafers, then you deposit a double layer, and that's something that is also very common for a lot of solar cell technologies, that your contact is often two layers. So there is a cadmium sulfide zinc oxide combination in CIGS, there is the cadmium sulfide tin oxide for the cadmium telluride solar cell. So you have, in a simple picture, you would say, okay, I need an N-type and a P-type material, and that's it for, okay, that's the back junction. But anyway, you often have this thin layer. Also here is a thin layer that has this purpose to enhance the selectivity by making a passivation for the minority carriers, so that nothing happens to the minority carriers, but still allow the majority carriers or the desired carriers to get through. So that is why you have this undoped amorphous silicon. And from the amorphous silicon world, it's very well known that if you dope amorphous silicon, it has no photovoltaic quality. You only use doped amorphous silicon for having the doping, for having the contact. But if you want to have something that is photovoltaically active, just keep out the dopant atoms, keep out everything. The poorer you are, the better your amorphous silicon is. And it's very clear that the surface passivation of the wafer can only be achieved if you have an undoped amorphous silicon. And that way you do also the PN junction. So starting here with an N wafer, you have on both sides this intrinsic passivation layer and the doped contact layer. And then of course, because this must be this is a light side and you have no conductivity from the emitter right now, you need TCO to have the lateral conductivity, and you have the and then now you see there is no more contact from the metal directly to the silicon absorber or base material. So that's why it has especially high open circuit voltages. So there are a lot of issues with short circuit current density, because you have not perfectly transparent layers on top compared to a normal silicon solar cell, where the first absorbing material the photon hits is already the crystalline wafer. So that's nice with the PERC and TOPCon technology. But here you have TCO and also the doped amorphous silicon, which even though they are very thin, doped amorphous silicon maybe only 10 nanometers, but already 10 nanometers can harm your JSC, your short circuit current density, and the TCO with the free carrier absorption is also. So, but for the VOC is very nice. So there's almost you can really get in VOC to the. You already clearly see the limitation by the Auger process inside. So the VOC is given more or less already at the limit. Other thing is, okay, you need no high temperature processes, and it's compatible with using the cheaper copper instead of silver in the contact material. And you can do this again, because copper you would like to avoid a lot in the silicon material, because that's really a bad recombination sender, so no way to bring the copper directly on the silicon, because in 20 years, even at moderate temperature, copper will diffuse. Copper is diffusing like hell in silicon. Sometimes you think if the wafer is here and the copper is there already, it gets contaminated. So that's, but it's efficient. So you have separated copper from the silicon, and you can use the copper in. Okay, and then back to the roots now. The IBC, you see now we having going also back a little bit to the photolithography, but okay, so there's a lot of steps, and also I'm a bit concerned about the time, so you need a lot of things to do to get finally, okay. Now you're having both, no, not yet. Oh, this guy has done a lot of work. Yeah, I think it was his PhD. Okay. Okay, now it's done. Okay, so you have. That's a normal IBC cell. Okay, that's the sun power cell. Okay, that's okay. There's still it's going back to the Perk principle, or to all that, having the metal on the semiconductor. You see how much work it is to get rid in a good way without loss of VOC, and having a good fill factor to get both contacts on the back. And the advantage, of course, then is you have nothing on top, and you have a very high JSC at that point. But now we still back here with a back contacted solar cell in an optimized way, and then you can compare the process if you do the IBC. IBC stands for interdigitated back contact, so that's the scheme here, that the fingers for both types just interdigitated here. You can do this with heterojunction as well. I see also a few process steps, but in the end you okay, that's what you finally get. You get this Pi and Ni separated from each other, so there should be no contact here, because then you would have a short between your contacts, so there you would bypass the solar cell. Everything should go through the solar cell, so that should be insulating. Yeah. I'm not quite sure whether that's also, I was asking myself at the moment. I mean, maybe it's just because those guys have this technology and nothing else. But you can, of course, do, it's more, much more reasonable to have something that is more transparent on top, so you can do the aluminum oxide passivation, or silicon nitride passivation, to have this scheme. So that's not optimum yet. So still, okay. Okay, so I have to speed up a little bit. It's just more or less the summary of what I have talked about with all this. So you can see it's all on a very, very high level and very close to the limits. And in industry, of course, it's a question whether how cheap you can do this production, how many process steps, what is cost of your equipment, capex, and all that stuff. Efficiency-wise, okay, clearly with the IBC, there's a 1% efficiency, so it makes a difference if the cost is the same. So efficiency is a big leverage. but still see, okay, that's a perfect understanding or the, no, perfect, but say the really necessary understanding of physics that leads to devices that can go towards the limits. Okay, so that was 26 is not the limit, so it goes a little bit further also with the TopCon in the recent years. So that's just making an update. So that's now in terms of Venn diagram. I already drawn that with the tunnel oxide for the TopCon with the heterojunction where you have the amorphous silicon, so the electrons can still don't need to tunnel through the amorphous intrinsic amorphous silicon, and that's a classical oxide. But of course, you see there is no way out. With a classical thick passivation oxide, you need the holes to get the holes to get the holes through. In this case, holes to get the electrons through. Okay. Still, there are losses. We are not at the limit. We are very close. A few loss processes that are important to consider is okay that still the light trapping and scattering can be improved. The reflection can be improved. Of course, the shadowing of the contacts is an issue because that's you're losing 3, 4, 5% of your area simply because you have the front contact. So there can make it more conductive and make it higher, better aspect ratio to get the area smaller. That's a lot of details you have to consider. Material options, and that's now coming a little bit closer to what we're doing in Jülich. So is there maybe a way to having new materials inside the game that, for instance, if you want to replace the doped amorphous silicon with another material that's more transparent. So, I mean, the amorphous silicon has 1.6 band gap energy. That's not really what you want to have on top of your solar cell as a layer that is not contributing to the short circuit current. So one idea is to replace this material by silicon oxide, but in that case a very non-stoichiometric silicon oxide. So that's not an insulating layer. So it must be conductive still, of course, but should be more transparent. And what we're doing is just if you deposit amorphous silicon, you can change the gases a little bit at CO2, which then makes silicon oxide partly, and also changing the position parameter so that you're not getting amorphous material, but that you're getting what is denoted microcrystalline or nanocrystalline materials. And that what is running under microcrystalline, nanocrystalline materials actually are always mixtures of materials. So, and that's what you have here. You have still pure silicon here. That's the nanocrystalline silicon. That's what you have in black. You still have amorphous silicon, and you have amorphous silicon oxide. So in principle, that material which runs under nano or microcrystalline SROX is a mixture of three different materials. And it's also like this typical compromise. If you having not the perfect solution, you try to mix something that has both, the one component has one desired property and the other component has the other desired property. So in that case, the conductivity stems from the essentially from the nanocrystalline silicon, and so still there should be a good amount of them, and you're getting more transparent because you have this amorphous silicon oxide that is not that much absorbing the light, and you can tune and optimize the thing, and you can gain in short circuit current density as we are currently. So there's more material on that's a finished PhD from 2017. Very nice, very systematic work. It shows how, in principle, these two figure of merits that you have in this material is conductivity, and say the optical band gap is a figure of merit, one number that tells you how transparent your material is. The higher the optical gap, the less optical losses you have, and principally you want to be up there, and you see, okay, if you play around with a lot of parameters, it's not, you have to make a compromise. You cannot go straight there, but you can go somewhere in that range, and then you're looking how much conductivity do I need to. We've learned also that conductivity, mobility, all these things that have to do with transport are critical values. So if you're above a certain threshold, you're fine. And the threshold here is somewhere here for that material is 10 to the -3 as far as I remember. So this material has a very high conductivity, but you don't need so much conductivity. So you're working on having more transparency and still having enough conductivity to have this thing working. So you see, the guy did a lot of depositions, much more than the rest of the literature. So that's okay, and also made nice analysis to see how the structure is of this material, where the doping atoms sit. So this a doped material, is it doping in the silicon oxide matrix? Is it in the nanocrystalline layers? But in principle it's in both. Okay, so that is improved since then at 21.4, so that's not like 25. But we now heading towards 23, 23.5, and still can preserve this higher conductivity, transparency, and if there is a way to get really also the top efficiency higher, you have to do something about the transparency on top. And you see that on the quantum efficiency, that you really can improve what is denoted the blue response by changing this the optical band gap as a parameter for the silicon oxide. So the concept is working, and I think that's yeah, of course.
So when you say of dark conductivity, it means conductivity without shining any light on it, right?
Did I use the term dark conductivity? When did I use it? Huh? Okay, yeah, that's exactly, yeah. I mean, for the doped material, there would not be a difference between dark and illuminated. That it's funny, yeah, that's coming from the tradition of the silicon thin film people. I mean, if you have amorphous silicon, it's so photosensitive that you have really to make very clear that it's dark conductivity, and should be totally dark, otherwise you're not measuring what you want to measure. In that case, I think he used it because he was in the group of the thin film people. So.
But then does it mean this conductivity is due to majority carriers, not
Exactly.
minority?
Exactly.
But then should we focus on like a minority here for solar too?
No, that's a contact material. That's the point. It's not photovoltaically active. That's only supposed to make the junction by being the p-type doped part and having a gap that is as wide as possible and should be as transparent as possible, because any photon that is absorbed in that layer is lost because of very fast recombination. And that's also why I'm thinking that makes, in that case, really no sense to use dark conductivity, because if you measure this highly doped material, there is no difference between dark and, because of the short lifetime. So that's very important to understand that we're talking about contact materials at that point. That should do one job, but not the initial photovoltaic job. So it just have to be the contact. So so other thing you can do is another material from related to silicon is silicon carbide. And that material has a really wide band gap of approximately, depending a little bit how to determine it, but at least 2.83 electron volts. So it's fairly transparent. And we can do it in a nanocrystalline way. And that's now really not a mixture of something. That's really silicon carbide and nothing else. And you see in that graph now there's no dark. It's simply conductivity now. If you compare this with all these silicon oxide alloys, you really get much better in that direction if you're going with the silicon with the silicon carbide. The bad thing about this material is that if you deposit it, the deposition conditions are so harsh that almost everything that is underneath is just gone away, etched away by a lot of hydrogen in the process. So it was very, very tough to use this material as long as you want to deposit it on something that is supposed to survive. But the properties are really excellent, as you can see. So it's orders of magnitude better than everything you can have with the silicon oxides. But then when the TOPCon idea came up, we had the idea maybe this silicon oxide, this stoichiometric, wet chemically grown silicon oxide, could be stable enough to withstand the deposition process. And in fact, it really worked. So the silicon tunnel oxide is still there. So we have this this TOPCon or this tunnel contact. Now there is no polysilicon on the other side, but there's just a silicon carbide on the other side. It's nicely N-type doped, so we can very well control this. And also if you look at the lifetimes, and it's so implied VOC of 720, so that's already something that is competing with what you can have in the classical or in the best passivated heterojunction solar cells. And I think we improved this meanwhile quite a bit. Yeah, okay, that's really 2 years old. I just would make, so we really are better. Okay, so that's another point here. You can tell that now we have not only the implied VOC at that point, but we have the really measured VOC at that point, and the efficiency that we have is 24% now. So we coming closer and closer to the world record. So, and that's, I think, very nice. I have no slide here. It's a very nice result because it's say new technology option that is only pursued by a small group, namely our group in Jülich, and they really brought it to a very very high level. Okay, so
maybe a short question.
yeah, of course. Where?
I see you have
Yeah.
here. I see you have hydrogen in the microcrystalline silicon carbide.
Yep.
Although I don't think you have hydrogen in the polycrystalline TOPCon contact.
That's another advantage of that technology. So
Can you introduce it and can have the classification?
yeah. I mean, that's if you go a little bit in the detail of the TOPCon technology. So how you make this poly layer to make it at high temperature, and then at high temperature, all the hydrogen that is possibly there went away. You know these problems also if you're going over that with your laser. So. And hydrogen is essential in passivating any defect that you have at the silicon interface. So if the hydrogen is gone, your passivation is gone. So that's on that level really matters at a very low density of defect state at the interface. I mean, you can see that at the band diagram. So if you have defects here, you don't care much about the selectivity here, but because the electron hole will recombine here anyway. And that's really a very, very critical issue because there's only few dangling bonds, so not matched bonds at that interface can spoil, destroy the entire thing. So you need to have hydrogen. For the TOPCon, if your hydrogen is gone during making the polysilicon, you have to reintroduce it. So you need another process step to re-establish hydrogen passivation of the interface. But in our case, in fact, there's plenty of hydrogen and the silicon carbide still there because it's a low temperature process. So it's and there is hydrogen in the deposition process anyway, and we don't need this step. So in principle, if you look industrially, we really is as simple as possible. You're making the silicon oxide, you're making the microcrystalline silicon carbide. On the long run, even because that's very conductive, maybe we can even get rid of the ITO, which would really be a big deal then because it's a cost factor. Yeah, and everything is fine. So that's really a nice result. So. Always a little bit fiddling around with what is about the whole contact. So that's really a thing that somehow you can establish that it works, but as we're talking about clear physical principles, the clear physical principle would say with the silicon oxide you have problems if you want to get the holes through. The same is true for the amorphous silicon passivation layer, because also the offset between the amorphous silicon and crystalline silicon is not really shown here, is somewhat asymmetric. So also intrinsic amorphous silicon is more likely to have holes penetrate through it, electrons instead of holes, but somehow it does work. So of course you see it here. So it's hard to get in the highly doped material. But the other thing is how you make contact to the TCO. So getting the hole here through, and because of the difference in the work functions, there must be another tunnel contact here, because there is no direct, you cannot go. You have to end up here in the N-type, so you make an N-type, P-type contact that should be ohmic in the sense for the majority carriers. And that's really a problem of fine-tuning, that you get here this tunnel recombination. That's said to be a tunnel recombination junction, because you're tunneling through the entire band gap in principle. So there's not only the Mont Blanc on top, but there is also hell below, which is, and below is on top for the holes. So that's a quite tricky situation. So there's a lot of fine tuning to get that here, and it's not very, it all look like a bit workaround, and you see that in practice. That's really a very old graph that I was for my very, very first PhD student 15 years ago on the heterojunction. You see efficiency fortunately is not there, so it was very low or relatively low. But what you see is typically deposition time that's going into the thickness of the layer, and the typical compromise that you have if if you have thin layers, your fill factor is okay, but you're really with a very, very low VOC. Okay, so passivation is not good. Maturity transport is okay. And then you go thicker to hope to improve the VOC, and you see, okay, if you make it thicker, okay, it helps. You're getting higher VOC, but then you see that this threshold effect. So that means you hitting the critical value for the conductivity of your layer, and all of a sudden your fill factor is dropping. And then if you look at the product here, you see that by these two competing effects, you're getting a very narrow process window where the product of the both is optimum, and that's the typical compromise, and that's, I think, really a big issue why you need a lot of experience to get reasonably high efficiency with the heterojunction solar cell, because you have to somehow master this narrow process window. If you're outside that range, you more or less lost because you have to have this compromise. So what is there as a further? So is there a way how we can make that more physically profound and not just compromising around with a thing that has, say, proven disadvantages? So, and of course, as we've learned that silicon oxide is good for to transport the electrons because of the band offsets. So we have to look for other materials that have analogous requirements for the hole. So we can ask physics, what would be a good, or material science, what would be a good solution in terms of band alignments to have, say, at least a chance to get to an ideal hole contact. And that's what you are doing here it's essentially in looking at the valence bands and conduction band of the metal transition or metal oxide materials, and you can then check what material would nicely align with the position of the bands in silicon, and then you come up, okay, there are some that are nicely aligned with the silicon. You can look for these, or you can look for these that fit with a conduction band minimum to your. You still have this tunneling issue, but either one or the other band should fit to that band edge, so you can get it perfectly done. And that's a lot of research going on there. Interesting, not yielding too much into very high efficiency, but showing very clearly that that's the right track to do. But then, of course, a lot of other issues come. how this can be passivated, how not only caring about the majority carriers but also on the minority carriers. So maybe, but that's one interesting solution. Okay, so that was the introduction to my presentation. Now let's get to the real stuff. Now, so I have still 20 minutes, if I'm right. So
I think you are not right.
Pardon? No. I have 5 minutes. Okay.
Yes, exactly.
Okay. That's. Yeah. No. I was making that decision that I think it's okay to have a bit more discussion on the technology and not going for the equations. You have everything in the file, so you can look it up more. It's appendix, let's say. Then so then I would be finished even 5 minutes before my scheduled time. Yeah, you were right. It was 8:45. Yeah. Okay. Then that's it. If you have any questions, you can ask now or later. Otherwise, I think we have a break right now.
Yes.
Okay.
So, do you have any questions?
Yeah.
You showed at the beginning how there was like back and forth in technology for the silicon solar cells.
Yeah.
I wanted to know for the industry, how much do they need to switch completely their fabrication methods and investment when they switch the type of solar cells?
Okay. I'm not a specialist in that, but a few things I can say. Okay. They say all what is going with the diffusion process, or what leads to PERC, and in a sense also to for the top con, which only replaces the back contact. So top con is at the back, so sometimes you get confused. So I think there is always it's a technology line in the sense that you gradually can exchange part of your equipment to get those improvements. And the other line is the heterojunction. You need totally different equipment. So there is not, if you own a big factory on PERC cells, you would have a hard time to. You just build another factory. You cannot gradually switch. And that's really, one issue in industry is about investment cost, of course. And I think for the TopCon success, which come really fast going into industry, one advantage was that you just had to add a little bit equipment to a running line to go from the PERC to the TopCon back contact, and that equipment is so, as far as I understood, okay, the making of the silicon oxide, they have different choices. You not only need wet chemical. That was the biggest issue because that's something that was not there in. But on the other hand, it's a standard process in microelectronics. So, but then to deposit the polysilicon, it's off-the-shelf equipment. But in the end, okay, it turned out okay. You can do that more or less on a running line, or at least, or you have 10 lines running, and you successively change the lines from the one type of back contact to the other back contact. That's said to be the advantage. And okay, heterojunction is a totally different thing. You have manufacturers that are specialized on this type of PCVD equipment. and there is this, say, ecotope of these manufacturers there, but that's different. So that's and one thing is really that at the moment, I think a big leverage for cost is in fact the cost of the equipment, and also for equipment makers, there is some say how it is called a large scale, what is it? The economy of scale, because if you have an investor who is building a 10 gigawatt factory, he needs having 50 lines. So each piece of equipment you need for one line is made 50 times. And there already the economy of scale for the equipment maker comes into play, because if you're making a single piece of equipment for a factory, it's another cost if you have the chance to make hundreds of them. And that's, I think, what is going on at the moment, is that with these very big factories also you get this economy of scale into the manufacturing industry. Yeah.
You mentioned that Auger recombination was much more common in highly doped
Yep.
silicon. Why is that?
That's because Auger recombination is you need is essentially a three particle. I think that's now my drawing on the slide was not good enough. So that's first step is that the one electron recombines with a hole and gives the excess energy to another electron. And then that relaxes. It's not important for the moment. But the kinetics is here that the rate is proportional. That's mass action law. So you have two electrons, or you can see the other way around for the holes. It works the same way. So you have n squared times p. That's why it is very sensitive on the amount of, because it goes with a square here, so it's not very active if n is small, and but it's very active then n is going. So on the other hand, you may write that in a different way. So that are your excess charge carriers that in the n-type they come on top of the doping. And because if you, anytime you're making an electron, you're making also a hole. So you can replace the number of minority carriers as well. And if you look there, okay, you see at the beginning it's very sensitive on doping. But in the end, if your delta n getting larger than that one, or you are just in a very moderately doped absorber material, it goes with delta n to the 3. And that's independent of doping, and that is giving you the Auger limit for the even undoped absorber material. So Auger comes 2 times. It comes when you have it in the highly doped region because of that one, but it comes also in the what is denoted high injection case, where the excess carriers are more than anything else in the system. Then you're running in this delta n to the power of 3, which definitely gives you the Auger limitation of the silicon solar cells.